Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the final pressure of a sample of CO2 gas that expands reversibly and adiabatically from 67.4 kilopascal and 0.50 dm cubed to a final volume of 2.00 dm cubed. Take gamma equals 1.4. The first thing you have to remember is this is a reversible adiabatic expansion process, right? We're told the initial pressure we're told that the initial pressure is basically 67.4 kilopascal, right? And we're told that the initial volume, V initial, is going to be 0.50 dm cubed, okay? And the final volume, so we're told the initial volume is 0.50 dm cubed and the final volume to be 2.00 dm cubed. We're also told that gamma is 1.4. And all of this information requires us to find the final volume. So the first thing you have to note is this. For an adiabatic reversible expansion, the formula you would be using is P initial times V initial raised to the gamma equals, or raised to the power of gamma equals P final times V final raised to the power of gamma. So when you have this, you cannot rewrite the formula in terms of P final to be P initial V initial gamma divided by V final raised to the power of gamma. And you can proceed in basically writing this as P initial, okay, times V initial divided by V final raised to the power of gamma. So rather than writing the gamma separate, you can combine V initial and V final by saying V initial divided by final, all of that information in a bracket raised to the power of gamma. So when you have this information right here, right, you can now substitute what you have. So this is going to be P final, okay, equals the P initial here is 67.4 kilopascal. So that would be 67.4 kilopascal, okay, times the V initial is just going to be 0.50 dm cubed, okay, divided by V final, which is 2.00 dm cubed, okay, and then raised to the power of gamma, which is just 1.4. So of course you cancel dm cubed. You now end up having P final, okay, equals 67.4 kilopascal, okay, times 0.50 divided by 2.00, we end up with 0.25 raised to the power of 1.4. So P final equals 67.4 kilopascal, okay, times 0.25 raised to the power of 1.4 is the same thing as 0.14359. So all of this information is going to be P final equals 67.4 kilopascal times 0.14359. So that's going to be equal to 9.67778 kilopascal. Of course, this question would have to be approximated. So we have to go to basically the approximation that we're supposed to use. We have to look at our question and see the parameters we're given and pick the lowest number of significant figures. So that's basically how you do it. We have three sig figs here. We've got two sig figs here, three sig figs here. We've got two sig figs here. So that means our answer would have to be approximated to the nearest two sig figs, or to just basically to two sig figs. So P final is actually going to be 9.7 kilopascal. So this is basically how you solve this particular question. If you have any question, please put in the comment section. If you have any concerns as well as suggestions for how to grow this channel or things you would like to see on the channel, please also put in the comment section. Salam and welcome everyone. So Today we're going to be working on the question on the screen that says calculate the final pressure of a sample of H2O vapor that expands reversibly and adiabatically from 97.3 torr and 400 centimeter cube to a final volume of 5.0 decimeter cube. Take gamma equals 1.3. So the first thing you have to do is this. We're told to find the final pressure, right? And we're also told that there is an adiabatic reversible expansion. Whenever you hear something like that, you have to start thinking of all the different properties that happen whenever you have an adiabatic reversible expansion, as well as start thinking about the formula. Then we're also told that the pressure was from 97.3 torr. So that's going to be P initial equals 97.3 torr. Okay. And we're also told the initial volume. So V initial is going to be 400 centimeter cubed. And then they told us V final is 5.0 dm cubed. And they told us the value for gamma is 1.3. Now, the first thing you have to note is this. For an adiabatic reversible expansion, what you have is P initial times V initial raised to the power of gamma equals P final times V final raised to the power of gamma. So therefore, P final is going to equal, okay, P initial, okay, times V initial and then raised to the power of gamma divided by V final raised to the power of gamma. Now, this is how you go from this formula to this formula. We did this information in terms of P final, but our work is not done. So to proceed, we end up with P final, okay, equals P initial times a bigger bracket, V initial, okay, divided by B final raised to the power of gamma. So when you have all of this information, all you have to do is just substitute, right? So you have P final, okay, equals P initial, which is 97.3 torr. So we're just basically substituting times V initial, which is 400 centimeter cube, and then V final, which is 5.0 dm cube. Before you go on to substitute, right, you have to remember this important information. You cannot multiply, add, or subtract or divide values that have different units. Like you cannot cancel out the units for volume, cm cube and dm cube, except if you convert both of this information to the exact same unit. So meaning I have to either go from cm cube to dm cube to make sure that the units are all in cm cubed or the units are all in dm cube in order for me to proceed. So what I'm going to be doing now is to go from cm cubed, okay, to dm cubed to determine whatever it's supposed to be. So you have to note that 1 decimeter cubed, okay, is going to equal 1000 centimeter cube. That's just basically the law. Since we've gotten that across, then we go from cm cube to dn cube. So we have 400 centimeter cubed is going to give you what? It's going to give you x. So of course, you simply cross multiply where you have 1000 centimeter cubed x equals 400 centimeter cubed times decimeter cubed, okay? So x equals 400 centimeter cubed decimeter cubed, okay, divided by 1000 centimeter cubed. Of course, you cancel centimeter cube, cancel out centimeter cube, cancel out centimeter cubed, cancel out 400, 400. So 4 divided by 10 will give you 0.4. So x is going to equal 0.400 dm cubed. So that's basically how that is. So basically, the V initial in terms of dm cube is 0.400 decimeter cubed. So now that I have that calculation done on the left, I just have to substitute it in here. So that's going to be 0.400 decimeter cubed, okay, divided by the V final, which is also in decimeter cube, which is just 5.0 decimeter cubed. And of course, raised to the power of gamma, all of that information is going to be raised to the power of 1.3. Well, the great thing about same units is that they both will cancel out. So decimeter cube cancel decimeter cubed. So what you end up with is just P final is going to equal 97.3 torr, okay, times 0.400 divided by 5.0 raised to the power of 1.3. So P final equals 97.3 torr times 0.44 um 0.400 divided by 5 would give you 0.08 raised to the power of 1.3. When you have 0.08 right here raised to the power of 1.3 and you input that information in your calculator, what you end up getting is just P final, okay, equals 97.3 torr, okay, and then the inputted value of 0.08 raised to the power of 1.3 is going to be times 0.037499. Of course, you multiply both 97.3 torr times 0.037499. So P final becomes 3.64 863 torr. Okay. And of course, we see that our question goes from 5.0. We have 5.0, we have 1.3. We see that the lowest number of significant figures is two significant figures in this question. So we're going to deal with this question up until two sig figs. So that would be P final is actually going to be 3.6 torr. So that is just basically the answer to this question. If you have any questions, please put in the comment section. If you salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the final temperature of a sample of argon of mass 12.0 grams that is expanded reversibly and adiabatically from 1.0 dm cubed at 273.15 Kelvin to 3.0 dm cubed. So we have the mass is equal to 12.0 grams. We're told that this is a reversible adiabatic expansion process, right? So we're told the initial volume is 1.0 dm cubed. And of course, because this is an expansion, there's an increase in volume. So the final volume is actually going to be 3.0 dm cubed, according to the question. We're also told that this 1.0, it happened at 1.0 dm cubed, right? The initial at 273.15 Kelvin. So the initial temperature becomes 273.15 Kelvin. And we're told from the question to determine T final. Now, I wanted to first of all mention something to you guys because this is an adiabatic reversible expansion. You have to think about like the formulas that you're supposed to use to solve the question, especially when they directly ask you what you're supposed to solve for, as well as the parameters are given to you in the question. So generally, the formula, right, for the final temperature in an adiabatic reversible expansion process is T final, okay, equals T initial, okay, times V initial divided by V final. All of that information raised to the power of 1 over C. Sorry, raised to the power 2, 1 over C. Making sure to understand that C is equal to the molar heat capacity at constant volume, okay, divided by the gas constant R. So that is how you determine C. So in this particular case, we're not necessarily given the molar heat capacity. Sorry, we're not given the value for the molar heat capacity, right? But we can always Google it and determine the molar heat capacity of argon, a monoatomic gas. The molar heat capacity for this question is CV, comma M, okay, equals 12.47 joules per mole Kelvin. So that is it. When you Google it, you're going to find that. Or there's like another formula for you to solve the molar heat capacity at constant volume. Is just going to be 3 over 2 times whatever the R is. So that's basically whatever is going to give you. So CV, comma M for a monoatomic gas like argon. Okay, a monoatomic gas is just 3 over 2 times 8.3145 joule per mole Kelvin. Like you can do that times the gas constant, right? You can do that, but you can just simply just Google the exact value. So anyone works. So in case you cannot like Google it like in an assignment, just use the 3 over 2 times R to get your molar heat capacity at constant volume. So that is what this equals. Anyways, moving forward, we have 12.47 joule per mole Kelvin. So determining what C is, now C is now going to be equal to 12.47 joule per mole Kelvin, okay, divided by 8.3145 joule per mole Kelvin. So of course you cancel out joule, mole Kelvin. So that would be C, okay, is going to equal 12.47 divided by 8.3145, which is just basically 1.5. So now we have that information written down. Now we have the value for C. So what we have to do is just simply substitute, right? We're going to substitute the V initial, the V final, the T initial, and the C value. So Substituting, what's going on? So substituting, we have T final equals T initial is just basically 273.15 Kelvin. Okay, that's T initial times V initial, that would be 1.0 dm cubed divided by V final, 3.0 dm cubed. All of that information or raised to the power of 1 over 1.5. So next, since we have similar volume units, all we have to do is just basically cancel out the volume. So we cancel out dm cubed and dm cubed. So what you end up with is just rewriting the information with the units cancel. We have T final, okay, equals 273, okay, 0.15 Kelvin, okay, times 1 over 3, okay, raised to the power of 1 over 1.5. So that's basically what you do. So 1 over 1.5 is the same thing as saying raised to the power of 2 over 3. So basically, right, 1 over 1.5 is the same thing as raised to the power of 2 over 3. So I'm just like rewriting that for you. So when you have this information, then you can just say T final equals 273.15 Kelvin, right? 1 over 3 raised to the power of 1 over 1.5. You can input this part of the information in the calculator to get 0.487, okay, 49. So that's basically it. So T final equals 131.31 68 kelvins, right? So, of course, since this is a temperature question, we're just going to answer this question in two decimal places because our information has given us this initial temperature value to be in two decimal places. So that would be T final is equal to 131, okay, 0.32 kelvins. It's also possible, right, in this particular question that you can just like work to the closest number of significant figures that you have. So that would be you putting this information basically in two sig figs, and that would look like this. T final is equal to 1.3 times 10 raised to the power of 2 kelvins. So this could also be your answer based on whatever you're given and like whatever method you use. Just make sure to write this information here is two decimal places, and then here is just two significant figures. So that's basically the answer to the question. If you have any questions, concerns, and suggestions, please put in the comment section. If you're a student who is trying to succeed in all your STEM related courses, whether you're in middle school, high school, and college, make sure you email me at shohabitutoring@gmail.com. I help students who want to succeed and be the best version of themselves succeed by them utilizing my services. There are tutoring, mentoring services available for students across middle school, high school, and college levels. So if you have any questions, please just don't forget to email me at shohabitutoring@gmail.com. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, calculate the final temperature of a sample of CO2 gas of mass 16.0 gram that is expanded reversibly and adiabatically from 500 centimeter cubed at 298.15 kelvins to 2.00 dm cubed. The first thing you have to note is that we're told that this is a reversible adiabatic expansion problem. So anytime you have questions like this, you make sure you remember that you're going to be dealing with a specific formula for this question. But before we discuss the formula, let us write all of the parameters that we're given. We're given the mass to be 16.0 grams. We're given the initial volume. Hence, we're told from 500 centimeter cube to 2.00 decimeter cube. So the initial volume is 500 centimeter cube. The final volume is 2.00 decimeter cube. And we're also given the initial temperature to be 298.15 kelvins. And we're also given our, that's all we're given actually. We're now told to find the final temperature. So what we're actually looking for is T final. So since this is a reversible adiabatic expansion, right, you're going to be using this particular formula I'm about to write, which is the final temperature is equal to the initial temperature times V initial, okay, divided by V final raised to the power of 1 over C. So we've gotten the initial volume, the final volume, and the initial temperature. So we have three parameters in this particular equation. But the only issue is that we don't know what C is. So if you don't know what C is, you're going to have to like determine what C is in order for you to properly substitute the values and solve this question. But before we go on to determine C, we have to observe that we're given one of our temperature questions in 500 centimeter cube, and the final volume we're given that in decimeter cube. So what you have to do is to first of all convert 500 centimeter cube to decimeter cube, or you can go the other way. You can go from decimeter cube right to centimeter cube, or from centimeter cube to decimeter cube. The most important thing is for you to note that the volume has to have consistent units, meaning the initial volume and the final volume have to have the exact same unit. In this particular case, I'm going to be going from centimeter cube to decimeter cube purposely for this particular question. So to go from centimeter cube to decimeter cube, you have to note that 1 decimeter cube is the same thing as 1000 centimeter cube. And we're given the V initial to be 500 centimeter cube. So we're going to put 500 centimeter cube right here. And we're going to put the unknown X. Basically, we're trying to go from centimeter cube to decimeter cube. Of course, you cross multiply to know what the value would be for X. And what you end up with is we're going to end up with 1000 centimeter cube X equals to 500 centimeter cube decimeter cube. Of course, you can cancel out the centimeter cube because those are the units that are consistent on both sides, and X ends up becoming 500 divided by 1000 decimeter cubed. Of course, with some simple calculation, we see that this is going to be 1 over 2. So X is actually going to be 0.500 decimeter cubed. So that's basically what the V initial is in decimeter cube. So we can just rewrite our V initial here up top to be 0.500 decimeter cube. Now, the next thing we're going to do is for us to determine the value of C, right? You have to determine the value for C. We know that that's very, very important in order for us to like input all the questions here successfully. So to find C, we have to note this information right here. Let me erase this work so that we don't have to go too far. So to find C, we have to note that the formula is CV, M divided by R. So this is the molar heat capacity at constant volume, as well as this is a gas constant. So we know the molar heat capacity of this particular question, CO2 gas, is going to be 28.2 joule per mole Kelvin. And now you may be wondering, this information was not given to us in the question. Like the molar heat capacity at constant volume for CO2 gas was not given. Well, if you have your textbook, you can go to the resource section of your textbook and you'd find this value, or you can just simply Google the question. Sorry, not Google the question. You can simply Google what the molar heat capacity at constant volume for CO2 gas is, and they're going to give you that value. So CV, M divided by R, and R is just 8.3145 joule per mole Kelvin. So when you have that, of course, you input your information in the calculator to get C equals, let's cancel out joule, mole Kelvin. So that would be 28.2 divided by 8.3145, and that's going to give you 3.392. So that's the value for C. That's the value for C, and that's what we're going to be inputting in this information. Now we've gotten C, we have our T initial, our V initial, and our final volume. So inputting our work in the calculator, inputting our information in the equation, we have T final is equal to 298.15 Kelvin, okay, times the V initial is 0.500 dm cubed, okay, and then our V final is simply 2.00 dm cubed. All of that information raised to the power of 1 over C, and then C is just simply 3.392. So 3.392. So T final is going to equal this. Before we go ahead, let's cancel out the units for the volume, and we're going to input this information in our calculator to get, I'm talking about this information right here. We're going to input that information in our calculator to get 0.66436, okay, times 298 kelvins, 298.15 kelvins. when we input this information in our calculator, we end up getting 198.0779 kelvins. And as you can see, our question for initial temperature was given to us in two sig figs. So we end up putting this information in two sig figs. So the T final ends up becoming 198.08 kelvins. So this is in two decimal places, just like our initial temperature was given. Now, it is also possible for you to write this in three sig figs because the lowest number of significant figures in this question, as we can see, 2.00500 as well as 16.0 are all in three sig figs. Maybe that your professor or your teacher, whoever is marking your work, wants you to write in three sig figs. So if you have to write it in three sig figs, what you end up with is just what you end up with is just 198 kelvins. And that's going to also be the answer for two final in three sig figs. So I wish you guys all the very best. Salam and welcome, everyone. So today we're going to be working on the question on the screen that says a sample of CO2 gas of mass 2.45 gram at 27 degrees Celsius is allowed to expand irreversibly and adiabatically from 500 centimeter cube to 3.00 dm cube. What is the work done by the gas? The value for CV, M for this question is 28.14 joule per mole Kelvin. So the first thing you have to note is for the solution, is for you to write out all the parameters that we're given. We're given the mass to be 2.45 gram. We're given the initial temperature for this particular question to be T initial to be 27 degrees Celsius. And we can just simply convert it to Kelvin because that's how we want our questions in thermodynamics. We always want it in Kelvin. So we can just say 27 plus 273.15. So that's just going to be T initial is going to be 300 Kelvin. Sorry, 300.15 kelvins. We have is allowed to expand reversibly. Okay, so we have an irreversible expansion as well as adiabatically from 500 centimeter cube to 3.00 dm cube. So this is an adiabatic reversible expansion process. So we have to keep that in mind. So we're going to put our information down. We have the V initial to be 500 centimeter cube, and we have our V final to be, so let me rewrite the V final. We have our V final to be 3.00 dm cubed. And we're asked to find the work done by the gas. So we're actually looking for W. Part of the question is to tell us the value of the heat at constant, the molar heat capacity at constant volume. And we're told that we're going to use 28.14 joule per mole Kelvin. Now, I want to mention this. This was not in the initial question. I'm the one giving you the value to use. You could end up going online or having a question and you're going to be giving a totally different value, but this was not in the question. This is the best value I thought we could use for this particular question. So you can go online and find the molar heat capacity for carbon dioxide, and it's going to be slightly different, but the 28 is still there, but the decimals after the 28 might be a little different. The next thing we have to do is that we're told to find the work done. In order for us to find the work done, we have to note that part of the formula for work done is for us to know the final temperature, because the work done formula is W equals the number of moles times the molar heat capacity at constant volume times change in temperature. There's no way for us to be able to find the work done if we don't have the value for change in temperature. In order for us to find change in temperature, we have to have the final temperature, and which we're not given. So the first thing is now write out the formula for final temperature. So let me just erase this right here. Formula for final temperature in a reversible adiabatic expansion process is just T initial times V initial divided by V final. All of this information raised to the power of 1 over C, where C is equal to the molar heat capacity at constant volume divided by the gas constant R. So that's basically what we're doing. I don't want anyone to be confused. I know I just said a whole bunch of stuff, but it's doable, right? It's absolutely doable. So let's find what our value for C is. We have the initial temperature given to us. We have the final volume given to us. We have the initial volume given to us. But the only issue is that our initial volume is in centimeter cube. We have to make sure that both initial volume and final volume are in the same units. So let me quickly solve what C is, and then we're going to convert 500 centimeter cubed to dm cubed. That has to happen in order for us to properly substitute. So C equals CV comma M. So that CV comma M is just what we're given, 28.14 joule per mole Kelvin divided by R. R, of course, gas constant, so that's 8.3145 joule per mole Kelvin. So you cancel out joule and mole Kelvin, joule and mole Kelvin. So that C is actually going to now equal, C is equal 28.14 divided by 8.3145 is just simply 3.3844. So that's going to be the value for C that we're going to use in this question. So yeah, that's basically it. So the next thing we have to do is for us to convert the initial volume. The initial volume, let's not forget, is V initial is, we're told it's 500 centimeter cube, and we're trying to go to decimeter cube. So now for us to do this, we have to remember that one um one um one decimeter cubed is the same thing as 1000 centimeter cubed. Hence, 500 centimeter cubed is going to give you what? Let's use the value. Let's use the unknown value x. So if we do this, we can cross multiply, and we end up with 500 centimeter cube decimeter cubed is equal to 1000 centimeter cubed x. So we're trying to find x, right? Let's cancel out centimeter cube here, because we're actually trying to solve for decimeter cube, and we have two units on both sides of the equal sign, and we can just simply cancel that out. So x is now going to equal 500, okay, decimeter cube divided by 1000, and that's equivalent to x equals to 0.500 decimeter cube. So that's basically the answer to that. So yeah, let's go up and write the V initial, the proper V initial that we're going to be using in this question. It's going to be 0.500 decimeter cubed. So of course, let me clean all of this part. We've gotten the value we need to get for this. We actually even have the value for C, so I can just write C up top here. So C is actually 3.3844. So I'll write that 3.3844. So I'm just going to basically substitute on this part. So T final is going to equal T initial, which is 300.15 Kelvin. And then V initial, substituting it, we have 0.500 decimeter cubed. Divided by, of course, V final, which is 3.00 decimeter cubed. All of that information is raised to power 1 over C. So 1 divided by C, that's 3.3844. So that's basically it. Let me rewrite this. What's the power of 1 over 3.3844? So, of course, cancel decimeter cube here, cancel decimeter cube. So C final is equal to 300.15 kelvins times this information here. This information here, you put it in your calculator, meaning 0.500 divided by 3 raised to the power of 1 over 3.3844. You have to learn to input complex information into your calculator, and input that in my calculator, I ended up getting 0.58892. So that's basically what I got. So that's the information here. Now I can now use this information here and multiply by the initial temperature here to find the final temperature. So T final is going to end up being 300.15 Kelvin times this information, which is 0.58892, and you end up getting 176.764 Kelvin. So this is what we're going to be using as the final temperature. Now, let's not forget that our work is not complete. Our work requires us to find the work done. So let's not forget that the formula for work done is number of moles times the molar heat capacity at constant volume times the change in temperature. We have the molar heat capacity at constant volume given to us, and we can find the change in temperature. But the issue is we don't have the number of moles. Well, we know that looking back at our question, we have a CO2 gas and we're told the mass. We have the mass, we can calculate the molar mass, and we can find, of course, the number of moles. So the mass of what we're given is 2.45. Okay, we have the molar mass for CO2, which I don't need to solve because we're above that process of writing that out. You guys can just solve it on your own or Google it. That'll be 44.009 gram per mole. Okay, so the mass is gram. So number of mole will be mass divided by molar mass. So that'll be 2.45 grams divided by 44.009 gram per mole. So cancel out grams, cancel out grams. The number of moles here would be 0.055670 mole. So that's basically how it's done. So the work done adiabatically would now be us substituting this information. So I'm going to end up with 0.05567 mole, okay, times the molar heat capacity and constant volume. Going back our question up top, we see that is 28.15 joule per mole Kelvin. So that would be, let me actually erase this information. We've gotten the number of moles that we need. So times the molar heat capacity at constant volume, we know that to be 28.14 joule per mole Kelvin times change in temperature. So T final divided by T initial. So we have our T final to be 176.764 kelvins minus the T initial. Going back to our question, we see that is 300.15 kelvin. So that would be minus, oh, what's going on? Minus 300.15 kelvins. So of course, W adiabatic would just simply be 0.05567 mole times 28.14 joule per mole Kelvin times negative 123.386 kelvins. So of course you cancel out the kelvins, cancel out the kelvins, cancel out the mole, cancel out the mole. So that would be W adiabatic is going to be 0.05567 times 28.14 times negative 123.386. So all of that information would be negative 193.291 joules. And of course, we have to go back to the fundamentals of what we know chemistry to be. We have to look for the lowest number of significant figures, and we're going to have to put our answer in that. We see 2.45, 500 centimeter cube, and 3.00 decimeter cube. All of this information is in 3 sig figs, so that means our answer is going to be in 3 sig figs. So W, work done adiabatically, or adiabatic work done is negative 193 joules. So this is the answer to this particular question. If you have any questions, please put in the comment section. If you have any concerns or suggestions, also put in the comment section. If you're a student who is trying to succeed in all your STEM related courses, in whether you're in middle school, high school, or college, make sure you email me at shahabitutoring@gmail.com in order for you to just book a free session and just learn about the services that I render. I help students who are trying to be the best version of themselves in their academic career to succeed in that particular goal, as well as in other academically inclined goals that they may have. I wish you guys all the very best. Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample of nitrogen gas of mass 3.12 grams at 23.0 degrees Celsius is allowed to expand reversibly and adiabatically. Remember, we have an expand reversibly and adiabatically in the question, and that tells us that we're going to be dealing with a reversible adiabatic expansion problem from 400 centimeter cube to 2.00 decimeter cube. What is the work done by the gas? So we're asked to solve for the work done by the gas. The first thing you have to note is this information right here. We're going to write out all of the parameters. So to solve this question, of course, we're going to write solution because we're starting to solve. We have the mass of gas that we're given to be 3.12 grams. We've got the initial temperature to be 23.0 degrees Celsius. We've got the initial volume to be 400 centimeter cube. And we've gotten the final volume to be, we have been given the final volume to be 2.00 decimeter cube. So 2.00 decimeter cubed. And we've also been told that we're going to use the molar heat capacity at constant volume for this particular question to be 20.81 joules per mole Kelvin. So we've given all of this information right here. And of course, we're told to solve for the work done. Now, the first thing you have to note is our temperature is given to us in degrees Celsius. We have to go from degrees Celsius to kelvins. That's how you solve any question in thermodynamics. So that would be 23.0 plus 273.15. So the T initial would just be 296.15 kelvins. So that is what we're going to be using in this question. Now, one thing I want you to note is this. For a reversible adiabatic expansion problem that involves the work done, we're going to be using the formula N times CV, comma M times change in temperature. So we are going to be using the number of moles, we're going to be using the molar heat capacity at constant volume, and we're going to be using change in temperature. But the issue here is that change in temperature requires us to subtract the initial temperature from the final temperature. But the question here is we're not given a final temperature, which means we have to solve for the final temperature. So that is basically the important thing. So before we can even do the work done, we have a lot more to do first. T final in an adiabatic reversible expansion has the formula T initial times V initial divided by V final raised to the power of 1 over C, where C is equal to the molar heat capacity at constant volume divided by R, the gas constant. So we've been given the molar heat capacity at constant volume, right? We know that to be 20.81 joule per mole Kelvin. And we know the gas constant is a constant. So that's going to be 8.3145. We can easily solve for the value of C. So C is now going to be 20.81 joule per mole Kelvin divided by 8.3145 joule per mole Kelvin. So of course you cancel out joules cancel out mole Kelvin. So C is now going to be equal 20.81 divided by 8.3145. We have that information to simply be putting that information in calculator. We're going to have 2.502. So that's the answer here. So that's basically what's going on here. Now you can think, oh, well, we have our initial volume, we have our final volume, we have our initial temperature. So initial temperature check, initial volume check, final volume check, and we have the value of C. Then we can just simply input all of this information. This is very true, but the issue with this is that we still have one more thing to fix. So let me write the value for C here quickly, 2.502. We have one issue to fix. If you notice our volume is not in the same unit. Our initial volume and our final volume are in completely different units. So you know that whenever you're dealing with calculation problems in chemistry, you have to make sure that the initial volume and the final volume, or the initial state and the final state, are always in the same unit, always have the same unit. So we would now go from centimeter cube to decimeter cube. You can either make sure that the initial volume and final volume are both in centimeter cube, or you can make sure the both of them are in decimeter cube. I am going to be making sure the both of them are in decimeter cube. So we're going to be going from 500 centimeter cube to whatever that value is in decimeter cube. So we have to note, we have to remember, I apologize, 1 decimeter cubed is the same thing as 1,000 centimeter cubed. Hence, 400 centimeter cubed is going to give you what value? So I'm going to be using the proportionality method to calculate this. I'm going to use the unknown x for us to determine it. So we have 400 centimeter cube dm cube is equal to 1,000 centimeter cube x, right? So solving this, we're going to cancel out centimeter cube. Remember, we're trying to solve for 400 centimeter cube in decimeter cube. So we have to cancel this. And also, both units are in both sides of the equation. So that will be x equals 400 decimeter cube divided by 1,000. So that's just going to be x equals 0.400 decimeter cubed. So our initial volume is going to be, V initial is actually going to be 0.400 decimeter cube. And this is what we're going to be substituting in this particular equation. So yeah, that's basically it. Now we're ready to substitute and continue with our calculation. So I'm trying to erase this. I don't know what's up with the eraser today. Okay, so yeah, it's working now. So inputting our information, we have T final is now going to be T initial. We know that to be 296.15 kelvins. The V initial is 0.400 decimeter cube. The V final is 2.00 decimeter cubed. We have 1 divided by the C value to be, the C value is 2.502. Yeah, that's basically it. So cancel decimeter cube, you end up with T final is equal to 296.15 kelvins. Now, this entire information I'm going to put in a calculator. If you don't know how to put in complex information in a calculator, start learning to do that. Start learning to plug in fractions and powers in your calculator, because that's how you can solve questions like this. You're not going to be doing the math in your head, especially if you're in a test. That's not even going to be easy for you to do, to be honest. So you actually do need a calculator. So this whole information, putting in my calculator, I'm going to get 0.52556. That's it. So the T final would end up becoming 155.645 kelvins. So that is basically how you get this done. This is basically how you solve this. So we've gotten the T final, and we know that in order for us to find the work done, which is actually what our question is, we have to have the T final. So rewriting the equation for work done. So adiabatic work done is equal to the number of moles times the molar heat capacity at constant volume times the change in temperature. We can solve for the change in temperature because we have T final and T initial. We know the value given to us for the molar heat capacity at constant volume, and we have the number of moles. Before we solve this one, let me quickly mention this. This is a question from a textbook, all right? I want you guys to note that we're not given the CVM value. It's possible for you to be given or to be using a different CVM value in your thermodynamics/physical chemistry class. So if you're using that, maybe your professor gave you a particular value to use, please use that. This value is actually correct. I use the resource. You can either use the resource section of your textbook. I use Google to find this one. So it's possible for you to be given 28 points, maybe 82 rather than 81. It's possible for you to be given 28 point something. Sorry, 20 point something. So just put that in mind that sometimes these values would vary, but that 20 points is going to remain the same. It's just whatever is after the decimal point, it is what can vary a little bit. So just put that in mind. But for this question, we're going to be using 20.81 joule per mole Kelvin. So next, we're told the number of moles times the change in temperature times the molar heat capacity at constant volume. We don't have the number of moles. We can solve for that, right? Because that's easy. We have the number of moles equals mass divided by molar mass. And we know that the mass of the nitrogen is 3.12 grams. So that would be 3.12 grams times the molar mass. And the molar mass of N2 gas is just 28.013 gram per mole. Now, note this. I'm not going to solve out the molar mass of nitrogen gas. By this point in time, this is like advanced chemistry, so you guys know how to do that already. If you want me to write that step by step, I think you can just easily Google it and you're going to find that the molar mass for nitrogen gas is 28.013 gram per mole. So yeah. So the number of moles, 3.12 grams divided by 28.013 grams. You cancel out grams. Gram per mole, you cancel out the grams. You have 3.12 divided by 28.013. And putting that in my calculator, I got 0.11138 mole. So this is actually the number of moles. So now we have the number of moles. We have all the other values. So we just have to substitute. So the adiabatic work done is actually 0.1138 mole, okay, times molar heat capacity at constant volume. So that's going to be 20.81 joule per mole Kelvin. So that'll be 20.81 joule per mole Kelvin, okay, times change in temperature, which is just 155.645 kelvins minus the initial temperature, which is simply 296.15 Kelvin. So yeah, the adiabatic work done is now going to be 0.11138 mole, okay, times, I'm rewriting it, 20.81 joule per mole Kelvin times 155.645 minus 296.15 Kelvin is the same thing as negative 140.505 kelvins. So of course you cancel out the mole, cancel out the mole, cancel out the Kelvin, cancel out the Kelvin. You cannot input all of this information in your calculator to be 0.1138 times 20.81 joules times negative 140.505 would end up giving you negative 325.665 joules. Now, if you go back to our question, you can see that we have the mass in three sig figs. We have 400 centimeter cubed in three sig figs and 2.00 in three sig figs. The lowest number of significant figures in this question is in three significant figures. Is in three sig figs, right? So what that is telling you is that we have to put our final answer in three sig figs. So what we end up with our adiabatic work done is going to be negative 326 joules. And this is the adiabatic work done for this question in three sig figs. If you have any questions, please put in the comment sections. Sorry. If you have any question, please put it in the comment section. If you have any concerns or suggestions, also put it in the comment sections. Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample consisting of 1.0 mole of perfect gas molecules with CV equals 20.8 joule per Kelvin is initially at 4.25 atmosphere and 300 kelvins. It undergoes reversible adiabatic expansion until its volume, sorry, it undergoes reversible adiabatic expansion until its pressure reaches 2.50 atmospheres. Calculate the final volume, the final temperature, as well as the work done. The first thing you have to do when you're given a question like this is for you to note that we're dealing with a reversible adiabatic expansion process. So when you have that information in your head, you would know the type of formulas that you're supposed to use to solve whatever you're given to solve, right? So you also have to know that this is a perfect gas molecule. So those two information that you're given, or the particular information that you're given that I've underlined, are the most important thing for you to start. Next, we're going to write out the parameters and see how we're gonna see what we're given and what we have to do to start solving. So we're given the number of moles to be 1.0 mole. We're given the heat capacity at constant volume CV to equal 20.8 joule per Kelvin. We're told the initial pressure is 4.25 atmosphere and the initial temperature to be 300 Kelvin. And then we're told it undergoes reverse adiabatic expansion until the pressure reaches 2.50 atmosphere. So 2.50 atmosphere is going to be the final pressure. So that'll be 2.50 atmosphere. And we're asked to calculate the final volume. So these are the main thing that we're supposed to do. So the final volume, okay, the final temperature, okay, as well as the adiabatic work done. So this is a very loaded question, and I want you to brace yourself because there's a lot to solve here. The first thing you have to do is for you to note that when you're asked to find the final temperature, there are some parameters that need to be there. To find the final temperature in an adiabatic expansion process, you need the initial temperature, the initial volume, and the final volume. And in this particular case, we're supposed to find the final volume. So we have to find the final volume to find the final temperature. And then when we have the final temperature, we can actually solve the adiabatic work done. So make sure you take your time to listen to this. But one thing you also notice from the questions that we're never given the initial volume, but we're told that we're dealing with perfect gas molecules. So I'm sure all of you already know where I'm going with this. It is the usual PV equals nRT, right? We know the pressure, we know the number of moles, we of course gas content is constant, and we know temperature. We can always find the volume. So what I'm talking about here is us making sure that we're focusing on the initial state. So we're gonna have P initial, V initial, N is going to be constant through the whole process. R is always constant through the whole process. And then as well as T initial in the adiabatic process. So V initial is now actually going to be nRT initial divided by P initial. So of course, we're going to substitute what we have. We have the number of moles to be 1.0 mole, okay, times the gas constant 0.08206 liters ATM divided by mole Kelvin times the T initial, which we know to be 300 Kelvin. All of that information divided by P initial, which we know to be 4.25 atmospheres. So of course, we cancel out the mole, cancel out the mole. This one is mole Kelvin. Cancel out the Kelvins, cancel out the Kelvins, cancel out the atmosphere, cancel out the atmosphere. So V initial is actually going to be 1 times 0.08206, okay, times 300 divided by 4.25, Okay, all of that information is liters. So yeah, V initial is now going to be 5.7925 dm cubed or liters. Note that liters and dm cube are exactly the same units. I know this question says liters, you can call it dm cube, you can call it liters, it doesn't really matter. So that's the first thing you note. So now we have successfully found the V initial because we actually need the V initial to be able to solve the V final in an adiabatic expansion process. So we have the V initial now to be 5.7925 dm cubed. First thing you always have to do. Now, the next thing you have to do is for us to solve the V final. In an adiabatic expansion process, there are going to be times where you'll be given just the pressure or the volume, and you're asked to use that information to solve for one of the parameters. So you have to note that this formula is excessively or especially important for you whenever you're solving adiabatic expansion process. You have P initial, okay, times V initial raised to the power of gamma equals P final, okay, times V final raised to the power of gamma, where gamma is basically the ratio of the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. Sorry, let me erase this. Looking at the question again, based on our formula, right? We have the initial pressure, we have the final pressure, we have the initial volume that we just calculated for. We don't have the final volume. We can determine the value for gamma. The first thing you note is like you're going to be looking at it like, what is going on? This kind of looks weird because if we're trying to solve for the V final, we have a gamma raised to the power of that, and it's going to make our equation more complicated. So one thing you can simply do is for you to multiply the top equation. This is just simple math. Multiply the top equation, or I don't know if it's multiply or just raise the top equation, right, to the power of gamma. So what I'm trying to say is this. Let me just explain it this way. I think that would be better. So P final, V final, gamma. So you can just make sure you put everything here raised to the power of 1 over gamma. And I think that would sort it out. So raise this one as well to the power of 1 over gamma. So when you do that, what you end up with is P raised to the power of 1 over gamma, okay, times V initial, okay, gamma divided by gamma equals P final raised to the power of 1 over gamma. I apologize for the sheep sound, but we're going to continue this lesson today. Multiplied by V final, okay, raised to the power of gamma divided by gamma. Of course, gamma divided by gamma will cancel out. And then what you have is just simply P raised to the power of 1 over gamma times V equals P raised to the power of 1 over gamma times V final. So that's basically it. So the new equation we're going to be using would be P 1 over gamma V, okay, equals, sorry, not P, P initial 1 over gamma, okay, times just V initial equals P final 1 over gamma, okay, times V final. So yeah, that's how you basically do the math. And since we're looking for V final, we can just rewrite this equation like this. So that would be V final equals V initial, okay, multiplied by P initial divided by P final. This both of this information raised to the power of 1 over gamma. That is how you do this. That is how you simplify a difficult formula. So hopefully this has been helpful. I try my possible best to explain this, but yeah, we got to keep moving. But this is basically how you get it, and this is the formula we're going to use because this way we have the V initial, we have the P final, we have the P initial, and we just have to determine whatever gamma is, and we can just simply substitute to answer the first part of our question, which is for us to determine the value of the final volume. So yeah, let's go back here. Let's go back here. We have gamma equals Cp comma m divided by Cv comma m. So gamma is equal to Cp comma m is also the same thing as Cv comma m plus r. So this is a short thing, right? You know that Cp comma m is equivalent to Cv comma m plus r. Or you can remember in a previous session, r is equal to Cp, comma m minus Cv, comma m. This is in your thermodynamics slash physical chemistry textbook. The gas constant is just basically the molar heat capacity at constant pressure, okay, minus the molar heat capacity at constant volume. This is a known formula, and that's basically what we're using here. So I'm just like writing this out for anyone who is confused how we got there. If you study your physical chemistry textbook, you're going to see that this is an actual formula, and there are questions that would require you to use this, just like we're using this now. So the gamma here ends up being Cv comma m plus r. So we can just do the simple fraction Cv comma m, right, divided by Cv comma m plus r divided by Cv comma m. That's how you do it. So gamma ends up being 1 plus r divided by Cv comma m. We don't need to stress this out further. We just know that gamma is the same thing as 1 plus 8.3145, okay, joule per mole Kelvin, okay, divided by whatever Cv comma m is. Now you would know that we're only given Cv, right? We're not given Cv comma m. But we also know that the heat capacity at constant volume, if we want to change it to molar heat capacity at constant volume, we just have to divide it by the number of moles that we're given in the question. The number of moles that we're given in the question is just 1.0 mole. So to get Cv comma m, you just have to say 20.8 joule per Kelvin divided by 1.0 mole, which is the same thing as 20.8 joule per mole Kelvin. So we can just put that here, 20.8 joule per mole Kelvin. So that's how it's done. So of course you cancel out the units, So gamma right here is the same thing as 1 plus 8.3145 divided by 20.8 is going to give you 0.3997. So hence gamma is just going to be 1.3997. So that's basically what this is. So you have the value for gamma now, and you can now basically substitute all of this information in your work. So yeah, that's basically it. That's how it's done. So V final is now going to be V initial, going back to our work. We know that to be 5.72, sorry, we know that to be 5.7925. So that would be 5.7925, okay, dm cubed times V initial, that would be 4.25 atmosphere divided by 2.50 atmosphere raised to the power of 1 over gamma. So that will be divided by 1.3997. So that's basically how it's done. So yeah, that's basically how it's done. So we have all of this information now, and we can basically work from here. So yeah, that's basically it. So of course we're gonna cancel our atmosphere. We have V final is now going to be 5.7925 dm cubed, okay, times whatever this information is in our calculator. So we're going to put 4.25 divided by 2.50, all of that information raised to the power of 1 over 1.3997 times 1.46094. So when you do multiply this, you have 5.7925 dm cube, our initial volume, times all of this information here. When you multiply together, what you end up with is 8.4625 dm cubed. So that's basically the final volume. So of course we're asked to find the final volume. And we have our question so far. The shortest number of significant figure is 2 sig figs, but we're not going to focus on that right now. But just so you're aware, if you were asked to write this particularly in 2 sig figs, you have the V final is going to be 8.5 dm cubed. But I wanted to mention this, since we're still going to be using this volume in further calculation problems, we're not going to use the estimated or approximated value. So we're going to be using the one with 4 decimal places, which is 8.4625 dm cubed. So the next thing you have to do is, for you, since you have found the final volume, you're going to find the final temperature, which is the second question to solve. So the final temperature for an adiabatic expansion problem has the formula T final equals T initial times V initial divided by V final raised to the power of 1 over C, where C is the molar heat capacity at constant volume divided by the value R. So the C value, when we calculate it, CV, comma M, the molar heat capacity at constant volume, we know that to be 20.8. And of course, we've got 1.0 mole of perfect gas. So that's going to be 20.8 joule per mole Kelvin. So we're going to have that here. So that would be 20.8 joule per mole Kelvin, okay, divided by the gas constant, which you know to be 8.3145 joule per mole Kelvin. Okay, so we cancel out the joule per mole Kelvin, joule per mole Kelvin. So C is going to be 20.8 divided by 8.3145. We end up with 2.502. So that is the value for C. So now we're lucky. We've done, so now we've done it the right way, right? So now we have the initial temperature, which is 300 kelvins. Like, yeah, we have the initial volume, which is 5.7925 dm cube, and we have the final volume, which is 8.4625, as well as we have the C value. So all we have to do is just substitute. So T final becomes T initial 300 Kelvin, okay, times V initial, which is 5.7925 dm cubed. So I have to go back and forth. 5.7925 dm cubed. And then as well as the final volume, we have that to be 8.4625 dm cubed. 8.4625 dm cube. All of this information is raised to the power of 1 over 2.502. So yeah, that's basically how it's done. So we have 1 over 2.502. So T final is now going to be, of course, cancel dm cube, cancel out the dm cube. We now have 300, okay, Kelvin times whatever this information is in our calculator. So we're going to put 5.7925 divided by 8.4625. All of that information raised to the power of 1 over 2.502. And when we do that, we end up getting times 0.8594. So the T final is going to be 300 kelvins times 0.8594. You're going to end up getting 257.82 kelvins. Now, I wanted to also mention to you that when you look at our question, you see that we're given our initial temperature in 3 sig figs. So you're going to be doing the exact same thing here. So T final is now going to be 258 Kelvin. So this is basically the answer to T final. Remember, the question requires us to find V final, T final, as well as the work done. So this is something you need to know. But before we go ahead, I want to make sure everybody's on the same page with the fact that we're just approximating the value for T final because we're asked to solve for it. We are not in any way, shape, or form going to be using the approximate value for that calculation. So that's just basically something I need to point out, because you don't use the approximated or estimated value for that calculations. You use the raw value, then you get to approximate your final answer. So next we have to find the adiabatic work done. Adiabatic work done has the formula, the number of moles times the molar heat at constant volume, okay, times the change in temperature. So work done, adiabatic work done is the number of moles. We know that to be 1.00 mole, 1.0 mole, because we're told that at the beginning of the question, remember, 1.0 mole, and the molar heat capacity is 20.8 joules per mole Kelvin. We're going to be using that because, of course, we're going to be dividing it by that 1.0 mole. So that would be times 20.8 joule per mole Kelvin times the change in temperature. So T final minus T initial. So that would be 257.82 kelvins minus the initial temperature, which is 300, right? 300 kelvins, right? So the adiabatic work done is just going to be, let's supposed to cancel out number of moles here, number of moles here. So that's just going to be 1 times 20.8 joules per Kelvin is just 20.8 joules per Kelvin, first of all, times 257.82 kelvins minus 300 kelvins is going to give you what? So the change in temperature is equals to negative 42.17. Basically, that's it.
Yeah, sorry. Yeah, negative 42.179 kelvins. So yeah, so let's cancel out the kelvins because don't forget it's work done. So we always have to check our units, and work done units is always in joules. So never forget canceling out your units. So 20.8 Kelvin times negative 42.179 is equal to negative 877.33 joules. So that's it. Now let's go back to our question. We're giving our initial question in two sig figs. So we're going to be putting our answer in two sig figs. So what this would look like is adiabatic work done is going to be negative 8.7 times 10 raised to the power of 2 joules. So this is basically the answer to the question. So if you have any question, make sure you put in the comment section. If you have any suggestions on topic we should cover in all STEM related courses for this channel, make sure you also put that in the comment section. If you want to be the best student in all your STEM related courses, make sure you email me at shahabitutoring@gmail.com. I help STEM students, whether they're in middle school, high school, or college, to succeed in all their STEM related courses. And I help them in terms of mentoring as well as in other areas of their academic career. So if you would want any of my services, make sure you email me at shuhabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.